Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is just to walk through a demonstration of how to calculate power. So in this example we have is some sort of crew needs to get this 2,000 kilogram load here lifted to the top of this building, which is 20 meters high. They're doing so by using an electric motor which is connected to a rope which goes over this pulley down to this load. So again, what has to happen is this 2,000 kilogram load has to start here and move up to position 2. And I think what I'll do here is draw a picture of it at position 2, if you give me a moment here. So I'm going to copy this. Boom. All right. So what we're going to look at or try to calculate is how much power is required by the motor to move this 2,000 kilogram load from the ground floor here to here, a distance of roughly 20 meters. All right, so power is rate that energy is transferred. So there's a couple ways it's calculated. It's equal to change in energy over change in time, or we can calculate it like this. Power is equal to work done over change in time. Either one is acceptable here because of the work done on the system and the change in energy are the same. I'm going to go ahead and just use this. Now, it's important to realize that what's happening here as this load moves up is that the potential energy is going up. So in this example, the work done on this load is increasing the potential energy of the system. So since we're dealing with potential energy, we should define a datum. I'm going to go ahead and do that. Lowest point in the diagram is typically a good place to do that. So I'm going to call this zero potential energy. Now I'm going to go ahead and calculate our potential energy at position 2. Potential energy is mgh, so that's going to be 2,000 kilograms times 9.8 meter per second squared, or Newton per kilogram, those are equivalent units on gravity, times h, 20 meters. I'm going to go ahead and calculate a value. And I get 392,000 joules. That's the potential energy of the system here at what I would call position 2. And here's the potential, and here is the system at position 1. So the power required is going to be change in energy over change in time. The 392,000 joules represents the change in energy of the system. So we're going to have 392,000 joules divided by, we want this to happen in a 30-second time frame. And I get about roughly 13,000, it's 13,066, I'm just going to round up to 13,070 joule per second, or 13,070 watts. Now, I'm going to convert this to a horsepower to put this into a number that most of us are more familiar with. There's 746 watts in 1 horsepower. So we've got this 13,070 joule per second. Oops, got enough. Yep, 13,070 joule per second, which is 13,070 watts. Times, I'm going to use this as a conversion factor. In 1 horsepower, there's 746 watts. And I get about 17.5 horsepower. So this motor right here has to be at least 17.5 horsepower, and you never want to overstress a motor. You know, I mean, definitely it should be more than 17.5. If we actually need to get that load up there in 30 seconds, we would definitely want to hook a motor more powerful than 17.5. But the 17.5 horsepower represents the bare minimum power requirement to get this load from position 1 to position 2 in a time frame of 30 seconds. Right? And how do we calculate it? Well, power is change in energy over change in time. So what we need to do is calculate the change in energy of a system. In this case, it's just the potential energy that's changing. The PE1 is 0 because we're at our datum. The PE2 is calculated right here, 392,000 joules. So the change in energy would equal the 392,000 joules. PE2 minus PE1, which is 0. And then the power, just divide by time because power is a rate of change. So 392,000 joules divided by the 30 seconds. There's our 13,070 joule per second, or watts. The rest of this is just a unit conversion. Hope this helps demonstrate how to calculate power. Have a great day.